So right now we need to find the volume common to two spheres if the center of each sphere lies on the surface of the other sphere. So to do this, first we need to visualize what this volume looks like. So to visualize this, first we'll look at the cross-section of each of the spheres in the middle. So if we do this, then we get two concentric circles. Each of the circles has a radius r, which we can represent by this arrow. And also the distance between the two centers is also r. So now that we can see this, let's take a look further at some other geometries of these circles. So this is also r, and this is also r. So if we remember our trigonometric triangles, then what we know from this is that if we have a triangle that's equilateral, for example, the same length on all three sides, then we know that half of this is going to be r over 2, and because of that, this middle height is going to be r times root 3 over 2. So this is going to be important later on. So now on to visualizing what this actually looks like. You can imagine each sphere as adding up a whole bunch of small circles. For example, if we want to imagine this upper sphere, we can start by creating circles with diameters equal to the lengths that I'm drawing right now, and adding all of those circles together till you get to here. And then we can go to this bottom circle and add up all of these circles whose diameters are lengths that I'm drawing here. And if you do that, you can sort of visualize what this shape in the middle looks like, or what this volume looks like. So if we draw out one of the circles, so let this be the x-axis and this be the y-axis. If we draw out one of these circles, then what we're going to get is a circle with the equation x squared plus y squared equals r squared. So if we draw the other circle here, then what we can do is we can find the volume obtained by adding together all the circles from r over 2 all the way to r. And we're talking about lengths on the y-axis. So if we do this, then we can multiply that volume by 2 to get the volume of this entire object. So to do this, we can set up our equation, and since we're taking the heights from the circle to the y-axis, we need to solve for terms in terms of x. So if we do that, we get the equation of this circle being x equal the square root of r squared minus y squared. And this is the equation of this semicircle right on over here. And this ignores the negative side of that. But we don't need that because all we need is the radius with which we can rotate around the y-axis. So if we want to establish an equation, what we can do is write down an integral. So the volume is going to be 2 times the integral from r over 2 to r, and it's going to be the integral of pi times the radius squared. The radius, of course, being the distance between this semicircle arc and the y-axis. So we're going to square this. So we get r squared minus y squared. And this is in terms of y. So right now we have established an integral, a definite integral with respect to y, and now we can solve it. So to solve it, what we can do is bring out the pi, and then take the antiderivative. And we can do that because of the fundamental theorem of calculus. So here we get r squared times y minus 1/3 of y cubed, evaluated at r and r over 2. And now we're going to get rid of some of the unnecessary things so that we can have a little more space for our calculations. So if we bring this over to the top over here, we can evaluate this definite integral by plugging in the values. So we have 2 pi times r squared y, and y is going to be r, minus 1/3 r cubed, and then minus this definite integral evaluated at r over 2. So this is r squared, r over 2, minus 1/3, and this is going to be r over 2, all cubed. So when we do this, we get 2 pi times, so this is r cubed minus 1/3 r cubed, so this is 2r cubed over 3. And inside here, we have r cubed over 2, r cubed over 2 minus r cubed, I don't know why I wrote a 3, okay, r cubed over 3 times 8, which is 24. So we can keep going and get 2 pi, and we'll make it equal to we'll make all of the terms equal to the lowest common denominator. So this is going to be 16r cubed over 24 minus, so we can imagine this as 12r cubed over 24 minus 1r cubed over 24, so that's 11r cubed over 24. So these 2's can make this 24 go to 12. So then what we're going to get is 5 pi r cubed over 12. Now this is the volume of the two spheres. So we'll just write that down again. 5 pi r cubed over 12.